Okay, we have discussed this wiener filter so far. So we've seen that if you apply some input sequence to a filter, linear discrete time filter with some filter coefficients W0, W1 and so on. So this filter generates the output sequence Vn, Yn, and then you have desired response Dn. So you find the difference between the two, you get error sequence Cn. And the objective was to minimize this error in the mean square sense. So we have defined a cost function for that, which is the mean square value of En. And then we have minimized this mean square error. We have got a principle of orthogonality. Okay. And then later on we have derived a set of equations which is called as the Wiener-Hoff equations, which gives the solution for this minimum mean square error. Okay. So for that we need two matrices. One is the autocorrelation matrix and one is P, which is a cross correlation matrix. So if we have R and P, you can find the Wiener solution using these equations. Okay, this is what we have discussed so far. Now we will turn our attention to some applications of Wiener filter. So there are many applications where Wiener filter is used, because we will just go through one or two applications. So we take one application on which is used in the digital communication, which is channel equalization. So what is channel equalization? When you transmit a sequence through a communication channel, this is a communication channel. So this channel may be a wired channel, it may be a wireless channel. Okay. So when you transmit some digital pulses through this channel, there is an effect of the channel which is called as inter-symbol interference. Okay, ISI. So this inter-symbol interference is because of the dispersive nature of this communication channel. Okay, and as a result of this interference, what happens that the pulses that you receive at the receiver end, okay, there is an overlap between the adjacent pulses. Okay, or more specifically, you can say suppose that from the transmitter end you have transmitted one pulse like this. Okay, so because of the dispersive nature of this channel, the pulse that you receive at the receiver is basically spread in time, maybe like this. Okay, so at some time, suppose that t is equal to 0, you have transmitted this pulse, so you have received this pulse after some time, and then we transmit next pulse after some time t. Okay, and again when you receive this pulse at the receiver, now what will happen, although if there is no overlap between the first and the second pulse from the transmitter, these pulses will get overlapped at the receiver. Okay, so basically when we are in the digital communication, so we are interested in basically finding the peak values of the pulses. Okay, so from these peak values we identify that okay, which symbol was transmitted from the transmitter, right? So when you sample after some, so what we do, you transmit a sequence of pulses from the transmitter, and at the receiver, when you receive the pulses, we sample these pulses with sampling time t, okay, which is the switching time. So when you receive this pulse, suppose you receive this second pulse after time t. So what you will get here is that at this point the peak value of this pulse is this, so you should get this value only, but due to this dispersive nature of the channels, the adjacent pulses, they are overlapped with this pulse. So as a result, the effect of these pulses will also come into picture. This is what is interstable interference. Okay, so in order to avoid this effect of interstable interference, we basically use an equalizer before the receiver, which is called as channel equalizer. Okay, so you have a device here which is equalizer. So the effect of equalizer is basically to neutralize the effect of the channel. Okay, or you can say that if suppose you have transmitted some sequence un from the transmitter, and then it goes through a communication channel and then through equalizer, and then you receive a, or you generate output sequence yn, okay, which is basically given to the receiver. Okay, so the purpose of equalizer is to equalize the effect of this channel so that this yn, it is basically a same as the transmitted sequence un. Or you can say that these two systems, the equalizer and the communication channel, so since they are in cascade, so as a whole this becomes a identity system. Okay, so identity system means with unity with a impulse response which is a delta, and so that your input and output is same. Okay, now how it is done, because we have transmitted some pulse even from here, so output of the channel will be different due to this interstable interference. See, interstable interference is different from this additive white noise that we are not considering. Okay, we are forgetting that there is no noise, we are just concentrating on this interstable interference part. Okay, so communication channel, output of this channel, and then the output of this channel is given as input to this equalizer, and for this entire system we want that the output of the equalizer should be same as the transmitted sequence un. Okay, so how you do that? Using the wiener filtering. Using the wiener filtering, what you can do is that for the wiener filter, this, if I model this equalizer as a wiener filter, okay, so this equalizer is basically nothing but a wiener filter with some filter coefficients. So I have one sequence, input sequence to this equalizer, which is the output of this communication channel. And for this wiener filter, now I need a reference signal also. So I have to give some reference signal to this, which is desired response dn, and then I will compute some error here en, which is the difference between the dn and yn, and you minimize this error or the mean square error. Okay, now when you minimize this mean square error, which is dn, which is difference between dn and yn, and what we do, how we supply this desired response dn, is it basically a exact replica of this input sequence that you are applying to this channel. Okay, so we assume that your un is basically equal to dn. Okay, it means what the transmitter is transmitting, that is basically known to the receiver. Okay, so dn is the desired response, which is same as un, and how you can do that, that we will discuss. So dn is equal to un, and yn is the output of this equalizer. Now when you minimize this mean square error en, so what you will left with in this error sequence is that when the error will be minimum, it means your yn is a very close approximate of dn. So yn basically provides an approximation of this desired response. Okay, and when the wiener filter operates in the optimum sense, or when it minimizes the mean square error, at that point this yn will be a very good approximate of dn. Okay, so if the error is, for an ideal case, if the error is 0, mean square error is 0, it means your yn is a exact estimate of dn. And since dn and un they are same, it means yn is nothing but simply your un. So output of equalizer will be same as what is input to this communication channel. Okay, so at that point the model of this channel and the model of equalizer, they will be just inverse of each other. Okay, so if I suppose model this communication channel, if its transfer function is h of z, so when the wiener filter operates in the optimum sense, its response or its transfer function will become 1 upon h of z. Okay, and since these two are then cascade, so the overall transfer function is unity. It means whatever signal you transmit from the input, the same will receive at the output. Okay, so this equalizer will cancel the effect of channel in that case. Okay, so how you can do that? Let us suppose that this equalizer, now equalizer is nothing but it is a filter with some filter coefficients. Okay, and we assume that it is basically symmetric filter of order 2n plus 1. Okay, so 2n plus 1 order means that it has filter coefficients starting from suppose minus n to plus n. This is the impulse response of this equalizer. So we have one coefficient h of minus n, then h of minus n plus 1, and so on, and h of 0, h of 1, 2 up to h of n. So total length of this filter is 2n plus 1, which is the order of the filter. Okay, so the impulse response of this filter, let us suppose it is hn, so I can write it as summation of hk del n minus k, k from minus n to plus n. So it is h0, h1, h2 and so on. So at n is equal to 0 you have some value here h of 0. Then for n is equal to 1 you have some filter coefficients h of 1, h of 2 and so on. Similarly h of minus 1 and so on. Okay, so the problem is now to find these coefficients in such a way so that if some channel response is given to you, how you have to choose these coefficients so that the output of equalizer will be same as the input to the channel. Okay, so if this is the impulse response of this equalizer, similarly if let us suppose the cn is the impulse response of this communication channel, so I can write it as ck del n minus k, k from minus to plus n. Okay, so this is the impulse response of this communication channel. This is the impulse response of this equalizer. Now since these two are in cascade, this is your communication channel, and then in cascade with a equalizer. So un is input to the channel, yn is output from the equalizer. Okay, so its impulse response, I am saying that it is sorry, it was Cn, and the impulse response for this is, let us suppose Hn. Now since these two are in cascade, what will be the overall impulse response of the system? So these two in a combined way, it can be assumed that this is a one system or this is a single system. Okay, and since the two systems are in cascade, the overall impulse response of this, let us suppose I denote it W, it is the convolution between C and H. So convolution between C and H, you can write it as convolution of, that is H of K into C of L minus K, K from minus to plus N. Okay, L from 0 plus minus 1 up to plus minus N. So this is a simple equation of convolution. Okay, Hk into C of L minus K summation. So this is the impulse response of this equivalent system, which is the cascade of the channel and the equalizer. Okay. Now let us assume that the input sequence that you are supplying to this communication channel, it is a white noise sequence with zero mean and unit variance. Okay, white noise with zero mean and unit variance. So we have already discussed what white process or what white noise is. Okay, for white noise, the power spectral density is constant, and its autocorrelation function that we have seen, it is basically 1 for L is equal to 0 and 0 for L not equal to 0. Okay, it means no two samples of this process, they are correlated. So when L is 0, so it is the autocorrelation at 0 lag, so that gives you the average power, which is unit variance 1. So if L is not equal to 0 for any other lag apart from this 0, the correlation is 0. So this is a highly random process, white process. Okay, and in the frequency or the power spectral domain, its PST is constant. And practically, basically, how you generate a white process, we generate it using a pseudo random sequence, which is called as PN sequence. So PN sequence is a very close approximation of a white process or white noise. Okay, so you have a white noise to this input channel, and then see, when we have said here that okay, we need a reference signal Dn, and this Dn is supposed to be equal to Un, it means at the receiver end you must have another PN sequence generator, and these two generators, they must be synchronized with each other. Okay, or the design of this PN sequence generator at the transmitter and the receiver, that must be same. Okay, so that whatever sequence is generated at the transmitter, the same sequence must be generated at the receiver. So this is how you can make Dn and Un equal. Okay, and this Dn, which is a pseudo random sequence, which is a very close approximation of your white process. Okay, so assuming that Un is a white noise or white process, so the correlation for this sequence at lag is equal to L is equal to 0 is 1, and for L not equal to 0 is 0. And similarly, now since your Dn is equal to Un, since my Dn is equal to Un, so what will be the correlation or cross correlation matrix PL? Okay, so this is PL. You see, in the wiener filters we have seen two matrices because we are trying to find this solution for this equalizer. So you have to apply this R WO is equal to P. Okay, so R is the autocorrelation matrix of the input sequence, and P is the correlation between the input and the desired response. So if we have assumed that the input is a white process or a white noise, so its correlation matrix will be like this. So at L is equal to 0, its autocorrelation is 1, assuming that it is a unit variance, and for L not equal to 0, its correlation is 0. So if you basically find this matrix R, so this matrix or the autocorrelation matrix that we have discussed, so these diagonal elements, they are R zeros, R0, R0, and so on. Then you have R1, R2 up to R of minus 1 and so on. Similarly, R of minus 1 and so on. Okay, so all these elements will be 0 except this diagonal elements. So you have basically the correlation matrix R that you will get from this. If your input is a white noise sequence, you will get only a diagonal matrix in which all the diagonal elements are unity, rest all the elements are zeros. Similarly, you have to find this correlation matrix, cross correlation between dn and un. Now since dn is equal to un, so if you find the correlation between these two at any lag L, so this is equal to the autocorrelation of un, isn't it? So PL will be same again, it will be 1 for L equal to 0 and 0 for L equal to plus minus 1 plus minus 2 and so on. So for other lags, this correlation is again 0. So this matrix P, which is a column matrix, it will be again a matrix of 0. So at P0, which is 1, then P of 1 is 0, P of 2 is 0, 3 and so on. Similarly, P of minus 1 is 0, P of minus 2, everything is 0. So only P0 at lag 0, your correlation is 1. Okay. So R is now given to you. If you assume that input sequence un is a white sequence and the desired response to the wiener filter is a replica of this input sequence, so R and P will be given by this. This is R, this is P. Okay, and then RW naught is equal to P. So from this equation you can find that what will be the solution for this W, which is R inverse P. Isn't it? So if you multiply this R with filter weights to get this matrix P, so in the P I have again 0, 0, zeros, then 1, zeros. So here I will have filter weights W minus N, W0 up to WN. Okay. So this is 2n plus 1 order, 2n plus 1 rows into 1 column. Similarly, 2n plus 1, this is also 2n plus 1 into 2n plus 1. So if you solve this equation, what you will get? You will get only one point where W0 will be equal to 1, rest all will be zeros. Okay, so alternately by applying this wiener filter equation, you will have, okay, that WL will be equal to 1 if L is equal to 0 and it is 0 for L equal to plus minus 1 plus minus 2 and so on. Okay, this you have obtained by applying the Wiener-Hoff equations. Okay, now this is my WL, and WL basically was the convolution between channel response and this equalizer. So channel response, we have said that okay, it is Cn. Equalizer response is suppose Hn, and WL, which is the net response of this cascaded system, was the convolution between the two, so which was summation of Hk C of L minus K. And by applying this Wiener-Hoff equations, that RW is equal to P, we have just found a solution for W, that WL should be equal to 1 if L is equal to 0, and it is 0 for L is equal to plus minus 1 plus minus 2 up to plus minus n. Okay, it means for this filter output to be same as the input, or this equalizer to equalize the effect of this channel, the overall impulse response of the filter must be like this. Okay. So in place of WL, you can write these equations on the left hand side and you can equate to zeros. So you will get summation of HK C of L minus K, K from minus N to plus N is equal to 1 if L is equal to 0, and 0 for L is equal to plus minus 1 plus minus 2 and so on. So by expanding this, you can get a set of equations. If you put those equations in the matrix form, so you first put L is equal to 0, okay, and then you vary K from minus N to plus N, you will get one equation. Then L is equal to 1, again vary K from minus N to plus N, another equation, and so on. Okay, so you can alternately put all these equations in the form of a matrix. So we will have one matrix of 2n plus 1 cross 2n plus 1, which will have this impulse response values C0, C0, diagonal elements will all be C0, then C minus 1, minus 2 up to so on up to C of minus 2n. Similarly here will be C1, C2 up to C of 2n. In the second matrix will be the matrix of H, the impulse response of the equalizer. So you will have H of minus n and so on, then H of 0, then H of n. So it is 2n plus 1 cross 1 vector. That will be equal to, on the right side, you will have all 0 elements except when your L is 0. So for L is equal to 0, you have 1. Rest all elements they are 0. Okay. So if now the channel response is estimated to you, if channel response of this matrix is given to you, so from this matrix you can find that what should be the impulse response of this equalizer so as to equalize the effect of this channel. Okay, this is what is called as a zero forcing equalizer. Okay. So zero forcing equalizer means what? That since the impulse response of this overall system, when you have cascaded this equalizer with this channel, so the overall system that you are now getting, the impulse response of this system is at 1 for L not equal, L equal to 0, otherwise it is 0. Okay, it means the pulse that you receive basically at the receiver. Okay, so the time at which it was transmitted, at that time its magnitude is 1. For all other sampling intervals, it will be 0. So the contribution from the previous pulses or adjacent pulses will be 0 basically. This is what is the meaning of this. Okay, this impulse response WL is 1 for L is equal to 0. So you have only one pulse here at L is equal to 0, rest it is 0. Okay, so when you transmit any signal from this and you find the convolution of this with this, so the adjacent pulses, their contribution will be 0. Okay, this is what is called a zero forcing equalizer. Okay, so it forces the response of the adjacent pulses to be 0 at the sampling instance, all other sampling instance except at the time at which the pulse was transmitted. So it will be like this. So you have one pulse, you will have one pulse like this. The second pulse that you have transmitted, suppose at t, it will be like this. Okay, so when you sample the second pulse which was transmitted at t, at that time all other pulses, this pulse will be going through 0, the next pulse it will also be going through 0, so their contribution is 0. Okay, As a result, whatever symbol you have transmitted from the transmitter, the same you are going to receive at the receiver. Okay, this is what is zero forcing equalizer. So the receiver, when it samples this received signal, okay, when the receiver receives the pulse and it samples it at a particular time, the contribution from the adjacent pulses is zero at that time because of this type of impulse response of this channel and equalizer in cascade. This is what is called as a equalizer, channel equalization. Okay, this is how you can use wiener filter. But see, anyhow, there are many other applications. Another important application in the wiener filter is channel, or it's called a noise cancellation. Okay, so in the noise cancellation, what is the problem? That you have signal which is basically corrupted with noise. Okay, so some information bearing signal, suppose dn, and it has some noise which is added to it. Let us suppose right, this is vn, the noise component. So this is signal sn, which is dn plus vn. So dn is the information bearing part and vn is the noise component. So the problem is to estimate this dn from sn. So what you have hand is sn, which is a corrupted signal, and you have to use a wiener filter which gives you a estimate of dn from sn. Okay. See, you may say that, okay, since you have a signal which is buried in noise, so you can use a filter which separates this signal from the noise. So that is okay when if the signal and the noise, suppose if this is the signal spectrum and this is the noise spectrum in the frequency domain. Okay, this is your spectrum of signal and this is spectrum of noise. So if the signal and the noise, they occupy two separate frequency bands, then of course a normal filter, like we use a low pass filter for this. Okay, so this frequency will be passed and noise is stopped. Okay, so if the frequencies, they occupy separate bands in the frequency domain, so accordingly you can design a filter based on some frequency response criteria and you can filter the noise part, right? But there may be some situations where the signal and the noise, they occupy the same frequency band. So if this is the signal part, this is the noise part. Okay, this is spectrum of noise and this is spectrum of signal. Now since in the frequency domain they occupy the same frequency band, so if you try to remove the noise, you will also lose the signal information. So in such cases you cannot use normal frequency based filters to remove this interference from the signal. So the solution that you have left is either the wiener filters or you having these adaptive filters. Okay, so what do you do in this case? So you have a reference signal Sn, which is dn, which is a information, plus vn, which is noise, and this we give as input to a wiener filter. And then we need here a desired response dn. Now the desired response that we give to the wiener filter when you use it for noise cancellation is basically noise, or I can say suppose it is noise is v1, so it is v2n. So v1n and v2n both are noise. Okay, but they are not exactly same. v1n is not equal to vn, but they are correlated. Okay, and then you find this error between dn and yn, and then you minimize this mean square error. Okay, so what you will get basically in this process, when you will discuss adaptive filters later on in detail, so you will see that this yn, which is the output of this wiener filter, okay, sorry, this I have given a wrong statement here. This Sn, which is dn plus yn, it is basically given as the desired response. This is here Sn, which is dn plus here v1n, and this input to this wiener filter is just a noise, v2n. So v2n and v1n, they are correlated to each other. The purpose of this wiener filter is basically to generate a output yn, which is a very close approximate of this noise which is present in this reference signal Sn. Okay, so that when you subtract these two, so this noise component gets subtracted from this noise component, your signal part, that is dn, will be left only here. Okay, so later on we will say that when you minimize this mean square error, so minimizing of this mean square error is basically equivalent to minimizing this difference, that is v1n minus v1n cap square. Okay, so in this process, if you minimize the mean square error, so minimizing the mean square error is equal to minimizing this. Okay, so when the filter operates in the optimum sense, in that case this error will be minimum. If this error is minimum, it means your output of the filter is a very good approximation of the noise which is present in the signal. Or in general, you can say that this wiener filter in here, its output that is generated, it is basically giving you an estimate of the noise which is present in the input signal. Okay, so when you minimize this mean square error, at that time, now in this case the error signal will contain the minimum mean square value of this dn. Okay, this will contain the minimum mean square value of this, not dn but this signal Sn, because this will be for a good wiener filter or for a good noise cancellation problem. What will happen if the dn, we assume that the dn and the v1n, they are uncorrelated, and if v1n and v2n, if they are correlated to each other, this filter will generate a response v1 cap n, which is the best approximation of v1n. And in the optimum sense, when you minimize this mean square error between these two functions, so this error will become almost zero. What we left in the error signal is only your dn. So this en will basically give a very close approximate of this information signal. Okay, so anyhow, again, when you need to find this wiener filter solution, you have to find this matrix R and then P, and then optimum solution you can find using this equation, Wiener-Hoff equation. Okay, but many a times this noise or the correlation of the input sequence or the correlation between the noise and the input is not unknown. Okay, so you may not be able to apply this Wiener-Hoff equations. Or when the signal is changing, it is non-stationary, it is changing its characteristics from time to time, so every time we have to find this Wiener filter solution. Okay, or you can say that if you have this Wiener filter solution, it means when you have this error performance surface, so you have a unique, it's a bubble type surface with the unique minima. Okay, so the signal statistics, they are changing in time, it means this shape will also change. So the solution will change in time from this point to this point, then this point to this point. So every time you have to apply Wiener filter or Wiener-Hoff equations. That is not practically feasible. Okay. So for those cases when the signal is non-stationary, it is better to use the adaptive filter. Okay. So the structure of adaptive filter and this noise, this Wiener filter is almost same, but the difference is that that you have, okay, you have some input sequence, you apply it to a filter, this filter generates some response, then you compare this with a desired response, you get some error, and then you try to minimize the mean square error. This is what we have done in the wiener filter. In the adaptive filter we do the same process, but we do not find the solution of this filter using wiener equations. We use a adaptive algorithm here, and this error sequence is basically given as feedback to this adaptive algorithm. And now these filter coefficients W0, W1, they are not fixed, they are time varying. And this adaptive algorithm, there is a mechanism to update these filter coefficients successfully. Okay, so at n is equal to 0, okay, you set some filter coefficients here, you don't know where is the solution, so you get some output, you will get some error, so that error is given feedback to this algorithm. It will like change this filter coefficients at next time. So at n is equal to, so if you have at some time n, you have some filter coefficients, at n plus 1 you will have another filter coefficients, and of course at that time the error will be somehow reduced. Then you still see, okay, this error is not minimized, or you have not attained this minimum mean square error. Again you feed back to this algorithm, you again change this filter weights. Okay, so ultimately after many iterations you reach to the solution of wiener filter. So the solution of adaptive filter, once the adaptation is completed, it is same as the wiener filter solution. Okay, but in this case you need not to find any correlation and the cross correlation matrix. Okay, so you'll see that there is an algorithm which is used here, which is called as least mean square algorithm, which is used for the adaptation of these filter weights, or in the more general we use method of steepest descent. Okay, and then that is basically converted to this LMS algorithm. Now if you use this type of structure, suppose for channel equalization, that we have taken example. So what you do in that, you have input signal, you have a channel, and then you have equalizer. Now this equalizer in this case is nothing but an adaptive filter with time varying filter coefficients. And now this DN sequence is basically what is given to your channel. Okay, this is we have seen that how you generate this. So you have a pseudo random generator, and the design at the transmitter and the receiver is same, so that these two sequences, they are just the exact replica of each other, or you can say what the transmitter is transmitting, that is known to the receiver for the time being. And during the learning phase or during this adaptation, when you generate some error sequence here by finding this difference, now this is given to a adaptive algorithm which will update this filter weights. This is the adaptive equalizer. Okay, so it adapts its response according to the channel response. Okay, in the previous equalizer that we have discussed, zero forcing equalizer, you must know what is the response of channel, then only you can find the response of this equalizer. But in this case you need not any information about the channel statistics or channel parameters. It will adapt itself in such a way so that the response of this will become equal to the inverse of the channel response in terms of transfer functions. Okay, so that the output of this yn is a exact estimate of what you have transmitted from the transmitter. Okay, this is what is adaptive channel equalizer. So this is done basically during the training phase. So you transmit a training pulse, which is a PN sequence that is known to the receiver, and the adaptive filter adjusts its filter weights so that it learns the channel response, and it adjusts its response according to the channel so that equalizes the effect of channel. And then this training sequence may be given time to time. Okay, because this channel is random, so its response may get changed after some time. So after every half an hour or maybe 1 hour, you again give a training. So in the training, you again give a pulse here or a spin sequence here, that is again given to this receiver. It will again adjust its filter weights. It will change its response in order to satisfy again this condition in match with this impulse response of the channel. Okay, Similarly, when you use adaptive filters for noise cancellation, so in that case again you have a signal plus noise Sn, which is dn plus pose v1n. Okay, so this is given as reference signal to this adaptive filter, and to the input of this adaptive filter we give only a noise component, now v2n, and then again you find the difference and you find the error, and then you feedback this error to some adaptive algorithm which will update the filter options. Okay, so in this case what is the advantage, that even if the noise characteristics they change from time to time, so the filter will adapt itself according to the signal characteristics. Okay, so that this en, it gives a good estimate of dn, the information bearing signal. Okay, so this is very widely used practical algorithm used in air-to-air communication for communication between the pilots in fighter aircrafts. Okay, so how we do that in that case? See, you have noisy signal, which is signal plus noise. Now signal plus noise means this is, in that case, will be your pilot speech, pilot voice, and this Vn is somehow the noise which is in the cockpit due to the engine noise or due to the air. Okay, so this is engine noise. So we have one microphone now here, and this mic will capture both these, which is close to this pilot, so it will capture pilot voice as well as the noise, and then you place one other mic in the cockpit which is away from this pilot. Okay, so that it somehow captures the noise only. Now this adaptive filter will provide you output which is the estimate of the noise which is present in this speech signal. So it will adaptively cancel it somehow, and error signal will give you a filtered signal which contains this pilot speech only. Okay, or it improves the signal to noise ratio. Okay, similarly you may use it for in other applications. So many applications are there, like for biomedical applications. So when you go for this fetal ECGs, okay, so when you take this abdominal ECG, AECG we call it as, which is a mixture of mother ECG plus fetus ECG. Okay, and then we, so in this case now fetus ECG is the signal and mother ECG is the noise, because I'm wanting or I'm trying to get this fetal ECG from the abdominal ECGs. And then you take here a chest ECG. Okay, so this chest ECG is basically now noise which contains the ECG of mother only, and this abdominal ECG which is maternal ECG, MECG plus fetal ECG. So this abdominal ECG I will give here, and this chest ECG I will give here. So this adaptive filter will cancel this maternal component. As a result, in the error part you will get only this fetal ECG. Okay, so there are so many other cases where adaptive, we will anyhow we will turn or we will come back to this adaptive noise cancellation once we will discuss adaptive filters in more detail. Okay, so to conclude with this, so wiener filter basically in the error performance surface, your mean square error is the m-dimensional function of the filter weights W0, W1 and so on. That is a bowl type surface with a unique minima, so that we have obtained using the gradient operator. Okay, which gives you the minimum value of the mean square error. So the same can be achieved using the adaptive filters. In that case, you start from any point on the surface and then this adaptive filter learns from the signal, and it basically goes on the surface. So this error goes on minimizing, and you converge at a point which is the solution of wiener filter. Okay, and after some time, if the signal statistics change, again this adaptive filter will change its filter weight so that it gives you the minimum mean square error. Okay, so in adaptive beamforming it is also used, adaptive filters or wiener filters. Okay, which is used in the space division multiplexers. So you have a array of antennas, and if you want to focus this main lobe in a particular direction, so that can be done using adaptive filters. Okay, so this is the direction of the main lobe of the radiation pattern of a linear array of antennas. So if you want to change this to this direction, so that can be done using adaptive filters, which is called as adaptive beamforming. Okay, so in spatial filtering, this is what is called as spatial filtering. Okay, we also use adaptive filters or wiener filters. So next we will discuss this method of steepest descent, and then we will come to this adaptive filters and this LMS algorithm.